Physics and Engineering in Kharkiv, Ukraine. Sergey, we hope you are safe now. And he will talk about strongly driven qubit resonance system, Landau-Zener-Stuckelberg-Majorana interferometry. So, Sergey, please.
Thank you, Andrei. Can you see my presentation?
Yeah, everything perfect.
Very good.
And we see all your group now.
Yes, it's my group.
Yeah.
And trying to exclude unneeded panels. Andrei told about my title. I am from Kharkiv, from Verkin Institute for Low Temperature Physics and Engineering. This is my group, and we do different problems on quantum dynamics, and in particular in relation to Landau-Zener transitions, also known as Landau-Zener-Stuckelberg-Majorana transitions, interference. I'll tell about this. And what I'm going to show you as our current research interests relates to qubits coupled to resonators. This is the problem resolved, which we are now trying to solve with Oleg Ivakhnenko. So, as Andrei said, I'll say a few words about the hardware. Then only a few slides about our particular system. I realized that I'm the fifth speaker today, so I decided not to tell too much technical details, and I will rather use my time, which I started to calculate. I will rather use my time to tell you about Landau-Zener transitions. So, about different qubits. In the previous two talks, the qubits were zeros and units. In reality, they look like this. And speaking about the question, which one wins, which one will win, it's not that clear yet. Diverse realizations have different advantages, and it's very nice that so diverse systems are studied. And in our case, my point is that all these are reduced to an effective two-level system. These all are described by pseudo-spin Hamiltonian. Josephson-Junction qubits, qubits based on semiconducting quantum dots, etc. And even classical resonators, they have something to do, some similarity with this energy structure. I'll show you three examples, which relates to what we did with our colleagues. A sort of a semiconducting qubit, a sort of a semiconducting spin qubit. This is realized in a tunnel field effect transistor with different gates. And what is qubit? It is the spin state in one impurity. And with this, the experimentalists observe different interferometric picture, of which I will tell more. This is the introduction just to show, to present different physical systems. They are diverse. This is another realization of a two-level system, not a qubit. The Chinese group, they realized a two-level system and the interferometric picture similar to the previous slide on a classical system comprised of mechanical nested ring resonators. My third example relates to Andreev bound states. realized on a nanowire with gates, and again, similar interferometric picture. So very diverse systems, and these pictures were here to show you this. What's inside an IBM quantum computer, which Christina uses? This is one example, Osprey quantum computer. There are qubits, wires, which carry input and output signals, and resonators. So essentially, qubits are coupled to resonators. And our aim now, the problem we solve, we study the qubit-resonator system in various conditions and within wide range of parameters, how these are controlled and read out. To relate this problem with what you probably know, I would like to say about an atom coupled to a photon field. So from quantum optics or in quantum electrodynamics, this light-matter interaction is one of the basic models. Here are the typical parameters: small size, large resonance frequency, coupling strength, and what's relevant is, in our consideration, is that this is small in relation to resonant frequencies of the atom. A completely different system, which otherwise behaves similarly, is illustrated here with artificial atoms, superconducting qubits, which are loops, superconducting loops with Josephson junctions. And this behaves as a qubit, as an artificial atom, as a two-level system. This is coupled to another one. These are biased by constant signal, these are driven by periodic signal, and probed by classical LC resonator. Just as one illustration of a characteristic micrometer size system analogous to what you know from quantum optics. Essentially, the coupling strength, what couples the atom to its surrounding controlling electronics, is not weak, but rather strong, or sometimes, as they say, ultra strong. So such systems not only require applying the mathematical and theoretical apparatus from the textbooks on quantum electrodynamics, but they require taking into account strong coupling to everything, to dissipative environment, to which is may be different in the morning and in the evening, to controlling electronics for the input of signal into a quantum processor, and also strong coupling to the output read out. So these are diverse, similar and diverse, these natural and artificial systems. And in a few slides, what we do, now we take the system, consider the system realized in circuit quantum electrodynamics. This consists of a flux qubit coupled to the transmission line via resonator. Such formulation of the problem is known as a two-tone spectroscopy. There are two signals driving the qubit: the probing weak one and the driving, which may dress the qubit. So the flux qubit is driven via the magnetic flux. It's the energy bias, which contains DC and AC component, which in practice help realizing logic gates, of which we heard in the previous talks. In our case, the qubit is driven, in the case of the experiment here, the qubit was driven via the third harmonics of the resonator. And this is described by the atom-photon Hamiltonian, atomic part, pseudospin Hamiltonian, photon part, where A stands for the annihilation operator of a photon in the resonator, coupling, probing signal, and driving signal. We do some transformations. In particular, we transfer to the instant eigenstates basis. And in this representation, we solve numerically the Lindblad equation. Then we obtain, as we heard, the density matrix with which we can calculate all the needed parameters. And in particular, we can have the photon number, the number of photons in resonator. In the experiment, this invisible value relates to what can be measured to the transmitted signal. And this is one of the examples which we call interferometry, what we calculate this photon number as a function of controlling parameters, energy bias, and the amplitude. And in showing you this, I'm going to the third part of my talk, where I will tell you how this can be explained in simple terms of Landau-Zener-Stuckelberg-Majorana transitions. These peaks, they relates to resonant excitation, and what interferes with what. One of the ways to describe this is to introduce you to the LZSM physics. So in the third part of my talk, I'll tell you which many of you, most or all theorists know as Landau-Zener transitions. Not many know about Stuckelberg and Majorana inputs in this problem. I'll tell you this interesting story, maybe in some sense pedagogical. These four scientists, interestingly, that year, all four of them were under 30 from 4 different countries, and the same year, without no interrelation, direct interrelation between them, they studied the very same problem of transitions in two-level systems. And interestingly, all 4 of them obtained exactly the same formula. Here it is, the formula. So let's consider a two-level system, which as a function of the bias. In the pseudo-spin Hamiltonian, we take this in that direction. This bias changes the distance between energy levels. It is minimal when it equals to delta at epsilon 0 equal 0, and it increases the energy difference. The time-dependent term, linear in the LZSM problem, moves the system from far to the left to far to the right, and the formula describes the probability to be excited. The probability is exponentially small, and this is the adiabaticity parameter with delta minimal splitting, and V, the speed with which we drive the system. For the repetitive process, if we drive the system not simply to the right, but also to the left, we have the time-dependent bias. Certain phase is accumulated, known as the Stuckelberg phase, and it results in the interference. All four these works are well known, and this table summarizes what was done for which system, which method. Does it describe not only the probability shown on the previous slide, but also the phase which is relevant for quantum operations, for quantum dynamics, for the interference which appears afterwards. And interestingly, only two of them, and these are not Landau-Zener, describe this phase. These are Zener and Majorana papers. And I will spend one slide to tell you about this work and two slides about telling about this work. And in particular, I attract your attention to that Majorana published the formula shown on the previous slide 4 months before Landau. And out of these many citations, paradoxically enough, this result, LZSM formula, is not the leading subject. Most or vast majority of these citations, they refer to the first half of the paper, where Majorana introduces what we know now as Majorana representation. So what I'm telling you now is the least known part of this work, the second one. So one slide about him. Enrico Fermi have put Majorana in one row with Galilei and Newton and called him genius. Majorana, who published only 10 papers, is known for very different things. And he is less known in this context of non-adiabatic transitions, which I'm telling you. So since he was the first and since he is not known, and because his derivation was interesting, and it was Frank Wilczek was interested in this and devoted to Majorana contribution the paper. I'll tell you about this more, mostly about Zener. So what we are speaking about is the Schrödinger equation with linearly driven two-level system. Alpha and beta are spinor components. Then these first-order differential equations can be changed to two second-order differential equations for alpha and beta separately, and the solution can be immediately written down. These are known parabolic cylinder wave functions. So here's the solution, which is probably the most known solution of the LZSM problem, because it is the analytical solution, not asymptotic, like in the case of Landau and Stuckelberg, and not approximate, like in the case of Majorana, which is still less not popular, but this is the analytical solution. But to do something with this, you either take the asymptotes of parabolic cylinder functions, or you solve or you find them numerically. So you return to the numerical solution of the Schrödinger equation. In contrast, Majorana's solution is asymptotic one, and we'll compare this asymptotic solution with the exact solution of Zener. Again, the Schrödinger equation, the spin, linear drive, then it can be transformed to the second order differential equations, somewhat different from the previous slide. And these are solved by the Laplace transform. Then using the inverse Laplace transform and the steepest descent method, the original solution, these functions, these components of the spinor are found. This is the circuit used in the steepest descent mode. Here's the solution. It looks quite bulky, but the advantage of this, in contrast to Zener's solution, that it contains only simple analytical functions. It can be easier analyzed. It is easier to take asymptotes, and also we checked its numerical correctness. So we can compare exact Zener solution and Majorana solution. And an interesting surprise for us was that it not simply correctly describes Majorana's solution, these formulas. They not simply describe the asymptotics at the infinity, but also give the transient oscillations. So only excluding very narrow region, Majorana's solution is numerically accurate. What we did, in addition to in our work, we also analyzed the case, what if we not simply start from the ground state, of which the solution is LZSM formula, but also what if we start from the superposition state, which is more complicated, but even here we found good agreement. And also in one slide, I would like to mention that in the LZSM problem, we can describe this alternatively, which can give you more insight, which can include our physical intuition, the adiabatic impulse approximation. This is the model which tells that the probability far from the avoided level crossing, where the energy levels approach to one another, the occupation probability is constant, then it in impulse type fashion it changes, and then remains the same. This is a very convenient tool which may help us understand physics better. So it's here how the initial state involves in the final one, starting from a superposition state to the left to the desired state to the right. This is described as the multiplication of the matrices: adiabatic evolution, impulse type transition, and then the adiabatic evolution again. Just a remark that this model is also used for describing completely different systems, phase transitions, known as the Kibble-Zurek mechanism. I'll return to the LZSM solution so that in 2 slides it becomes how and in what the interference results. Let us consider the upper level occupation probability as a function of time. We start from the ground state, where when the energy levels quasi-cross, we have the LZSM excitation, and when we second time make the levels meet during the periodic driving, we either have destructive interference or constructive interference. So we can have, on this diagram I show you, on this time dependence, single time LZSM transition, destructive and constructive interference. And now simple graph and diagram will show you this. This was during one period of driving when you have only two situations when the energy levels meet. And now I extend this to many periods. And then destructive interference is around 0, and constructive interference help you climb up to the unity occupation probability. With this Rabi-like oscillations, you can get 100% spin flip, not gate. So dynamics of the upper level occupation probability with repetitive passages is interesting and important for controlling system states. Simple animation, how destructive interference results in returning to the ground state, and constructive interference results in gradual increasing to the upper state here now with the 100 probability, and then with the 100 probability to the ground state again now. And this constructive interference can be interpreted as multi-photon transitions. When the energy levels are matched by either single photon or by multiple photons, we expect resonant excitations. And exactly we have this in theory. If I plot the upper level occupation probability, it is resonantly increased, dark blue color, along the lines described by this simple relation. From this, we can extract, this is a very important part of my talk, since it demonstrates how LZSM interferometric processes, they result in what in multi-photon resonances from which parameters of the qubits can be obtained. These oscillations, known as the Stuckelberg oscillations, they can help experimentators to calibrate the power which they introduce, and fine analyzing the resonance shapes can help obtaining relaxation parameters. So such beautiful agreement between theory and experiment allows in such problems make conclusions that this describes how the system, the individual quantum system, evolves from its ground state into any desirable superposition state. So this brings me to conclusions, which I make in 2 slides. If we have a two-layer system, we have the LZSM probability described by simple formula, and when this is done repeatedly, when you drive not linearly but periodically the system, which is nowadays possible with artificial systems, you can obtain increased occupation probability and the full control of such two-level system qubits. In particular, LZSM interference results in very rich physics, and now we study this not for isolated qubits, but rather for qubits coupled to resonators. And as one of the conclusions, not simply qubits coupled to driving fields are identical to the objects of quantum optics, but they have some differences. In particular, they have many levels, not only 2, and a qubit is an approximation when you take only 2 lower levels. You have to mind that the qubits are strongly coupled to the environment, and you may get the regime of strong drive. well. And now we study these strongly driven systems for qubits coupled to resonators, and we obtain such interferograms, which are useful for both controlling and measuring quantum systems. With this, I would like to thank you for your attention and advertise you our Kharkiv Quantum Seminar. You're welcome. Thank you.
Thank you very much, Sergey. Thank you much. Let's thank our speaker. And I believe we have some questions. Yeah.
Sergey, I have maybe technical question. You presented a solution of the Schrödinger equation in terms of parabolic cylinder function, and d depends on z and d depends on minus z. It is known that Wronskian of this function depends on the parameter, and for some parameters it can be zero, so function can be dependent. And there is another pair of the function called u and v, whose Wronskian is constant. Maybe it's maybe you don't meet the problem when your parameter lead to the function become dependent, but in principle, using u and v function might be more convenient even.
Probably yes. Indeed, the interesting point is that when z equals to 0, which is time equals to 0, which is the point where energy levels meet. I didn't think about that it can cause the problem. What we did, we compared this analytical solution with the numerical one, and we never had problems. We never had discrepancy between the solution, this solution, and the originally solving the Schrödinger equation. So I don't know how to comment on this. In principle, yes, this is built assuming that these are linearly independent, but in one point they become, this potentially might cause the problem, but this did not in our calculations never.
Okay, thank you very much. More questions?
I have a comment.
Yeah, please.
Yes. I have, of course, heard about Landau-Zener-Stuckelberg for many years, but today was the first time that I learned that Majorana solved this problem before Landau and Zener. So that was a new information to me, and it's very interesting that this information came from Kharkiv, Landau's first scientific city, so to say.
Yeah.
Yeah, thank you. Exactly, the work I mentioned was done when Landau was in Kharkiv, and he published the paper in the Soviet journal in German. One of our collaborators is Franco Noli, and with him, he is Italian, and so it was easy for us to discuss the text in Majorana's paper. Yes, but we are not the first. As I've shown you, also Frank Wilczek spent the whole paper discussing this, and in particular this novelty of Majorana.
Yes.
Thank you.
Okay, thank you. More questions? Yeah, okay. We don't have stupid questions.
Well, Sergey, thank you very much for very interesting talk. I have a very stupid question. You know, I am a stranieri in this area, stranger. Both you and Christina mentioned about the dependence of sometimes of the measurements, dependence of measurements on the day or night time. Where do the environment conditions come into your theory and analysis?
This comes from the fact that these are open quantum systems. You see, they are micrometer sized, and these wires, all these wires, through filters, they go to the room temperature. And the experimentators, they apply classical devices at room temperature, and they introduce signals. So with all this noise from what controls and what readouts qubit states, and this is difficult to describe theoretically, but probably how to describe open quantum systems. Diverse models can be used, like Caldera-Leggett model. And from the experimental side, they make very different efforts to isolate such system from dissipative environment, and this depends on how nicely they manage it, and probably look which is the effective temperature, which is the noise. All this varies depending on the conditions they have. So
Thermal noise or electromagnetic noise?
All the noises. The temperature is not zero here. Electromagnetic signals go here via DC and AC lines. There are magnetic fields, electric fields, even mechanical vibrations. So they put these refrigerators on very strong legs to damp mechanical oscillations. So it's a separate and very expensive technological system problem. Why such monsters as IBM and Google manage to realize this in experiments.
Okay, thank you very much.
So, one more question. Just a moment. Yeah, please.
It's not question, it's some comments. Alexey Vakhnenko, Boголюбов Institute. The Professor Davidov has used to say that there is no stupid questions. You see? Thank you very much.
Okay, but this is axiom. Okay, I see we do not have more questions. Yeah. And okay, I believe let's thank our speaker again. Yeah. I believe our program is complete. Yeah. On behalf of speakers, I would like to thank participants for being here. On behalf of participants, I would like to thank for speakers for